So the final is on the 19th, so on Thursday at 8 a.m. And we'll do the same sort of thing that we did on the previous midterms. So it'll be a 3-hour exam. You'll show up to Zoom at 8 in the morning, and you'll have 3 hours to take an exam that I will post on Sakai and that you'll have to upload to Gradescope. To help you study for this final exam, I would recommend that you do homework problems in the sections that we've been covering, but I'm also going to release last semester's third midterm. So this is going to cover material on like induction and modular arithmetic, stuff like that. So hopefully giving you last semester's third midterm will show you some of the questions that I liked to ask on those topics last year. I think those are all the announcements that I need to make today. Does anyone have any questions about stuff? I've been bad on reading my email, but I'll check and I'll respond immediately after this class. Sorry, Mahita. You mean, I mean, I already sent out, didn't I send out midterm 1? Oh, I probably only sent out midterm 2. I'll resend out midterm 1 again, sure. Any other questions or comments? Well, so what to say? I think that here's how I view the exams. The first exam is not really indicative of what's going on, in the sense that the first exam is all about logic, right? It's all on chapter 1. So I think that the first exam is this kind of weird creature where I have to ask you about truth tables and I have to ask you about all these logical like we obviously use logic a lot in this class, but we don't actually study logic anymore. We stopped studying logic after the first chapter. On the other hand, the second exam was more questions that I wanted to ask, but a lot of people got tripped up for several reasons about rigor on the second exam. And in particular, there were a lot of questions that revolved around the empty set on the second exam that people kind of got beaten up over several times, maybe. So I would say that the final is probably going to be, it's probably going to have similar questions to the second midterm. It's probably closer in questions to the second midterm than the first midterm, but I don't expect that you'll have as difficult of a time with it because you've already had that practice of the second midterm and you'll see what the my old third midterm looks like. And no cheat sheet for the logic part this time. Did that make sense as a description of the problems on the third, on the final? Yeah, it'll be proofs. There will be proofs for sure. I mean, you know that I have to test you on induction, for instance. That's a whole proof strategy that you haven't been tested on yet. But yeah, I mean, mostly this class we've been doing proofs, I think. Any further questions?
I think you said this earlier, but how many questions will it be?
I didn't say, and I don't know. Probably like 10 or 12. I'm not writing a 3-hour exam. I don't plan for it to take you 3 hours, and I'm not planning for a time crunch. And yes, I am doing office hours after class today at 10:30. Okay, so, and I'm also doing office hours on Tuesday and on Wednesday. So I'll come in on Wednesday morning at the same time as our class and just be in office hours. So, okay. Any further questions before we get started? It's been a long, strange, difficult semester. So I'm very appreciative of all of you for sticking with it and continuing to come to class. I've really enjoyed teaching this class, actually. Grading is less fun, but teaching it's great. Oh, one more thing. It would be very nice if some of y'all filled out teaching evaluations. Those are pretty helpful in general, but those are especially helpful this year due to the fact that I'm teaching this in such a different format and you're taking this class in such a different format. So any critiques and comments that you have on my teaching or what I could improve would be pretty valuable. I already have some ideas, like I need to be more disciplined about posting different things and stuff like that. But in general, teaching evaluations are quite helpful. So it'd be great if y'all could do some of those. Did someone have a comment? Okay, any last questions before I begin? Okay, so today I'm going to do some pigeonhole principle stuff. And this is probably all that you need to study up to for your exam. But then I'm going to go further and talk about permutations and combinations just because if I don't, it's a crime against the class. So you can kind of turn off your brains a little bit, I guess, when that comes. Okay, so I want to do two nice examples of the pigeonhole principle again, and to show that it can prove really interesting facts that might be really challenging to prove otherwise. So both of these examples comes from the book, so probably you've already read them. First example, let's show that if we have any n+1 positive integers not exceeding 2n, then one integer on the list must divide another integer on the list. Okay. Does anyone have any idea about how to approach this one using the pigeonhole principle?
I have a question.
Oh, sure.
So when I was doing the homework last night, um, it it did it in such a way that the pigeons were n+1. So would the n+1 be the pigeons?
Yes. Well, I mean, we have to figure out a way to phrase this problem so that we can use the pigeonhole principle. But so that's not clear just from the statement here yet. But in general, the pigeonhole principle says that if you have n+1 pigeons and they're trying to fit inside n pigeonholes, then at least one of the pigeonholes must have greater than one pigeon.
Can't you
Is that,
just divide anything by 1?
well, this is if we have any n+1 positive integers. So for instance, if we're talking about 2n, so let's take an example. Let's take n is equal to 3. So you're supposed to pick 4 numbers from 1, 2, 3, 4, 5, 6, right? You could avoid 1 and then 1 doesn't count, right? For instance, you could pick the 4 numbers 3, 4, 5, 6, but then the 3 divides the 6, right? Or you could
Oh,
pick 2, 3, 4, 5, but then the 2 divides the 4.
oh, I see.
Yeah, I mean, so mod is how we got how we had that very nice problem last time. What exactly was that problem last time? Oh yeah, it was showing that every number divides some number of the form with a bunch of 1s and a bunch of 0s. So for mod, I think here what I want to do is kind of close to mod. I want to essentially pick out the prime decomposition of my numbers. But I don't need the whole prime decomposition. I just need kind of 2 parts of the prime decomposition. So I'm going to let A1 have some prime decomposition, which means it's going to be 2 to the power of K1, right? Its prime decomposition has some amount of 2's, and that amount of 2's could be 0, times an odd number, which I'll call Q1. Now, in the prime decomposition, once you're done with 2's, every other prime is odd, and products of odd numbers stay odd. So essentially, I'm just saying, take the prime decomposition of my number, remember the 2's bit, and then remember the remaining odd number. And this odd number could be 1 if A1 is a power of 2, for instance. Do
Could
we
the
agree
odd
that this is,
number?
sorry?
Oh, I was gonna say, could the odd number be not prime because it could be multiple odd numbers multiplied?
Yeah, exactly. This could be like 3 times 5. So odd, but not prime. Is that okay? Now, if I write out my n+1 integers that are like this, all the way up to 2k n+1 q n+1, now what do I have? How many odd numbers do I have? We have n+1 odd numbers. I claim that all of these odd numbers are less than 2n, or less than or equal to 2n, because otherwise, if a qi were greater than or equal to 2n, greater than 2n, then 2 to the ki times qi would be also greater than 2n. So the ai would be greater than 2n. But we assume that all of the ai are less than or equal to 2n. So thus we see we have n+1 odd integers less than 2n. All of each odd integer is less than 2n. But how many odd integers are there that are less than 2n?
Would it be n amount?
Yeah, exactly. Because precisely half of the integers below any even one are odd. However, there are only n odd integers less than 2n. Now what can we say?
Would this be where you use the definition of the pigeonhole principle?
Yeah, I think here is where I use the pigeonhole principle. So by the pigeonhole principle, right, so Adele, I didn't assume that all these odd integers were distinct. I just assumed that there were a bunch of odd integers that are less than 2n. If I assume they were all distinct, then I would get a contradiction. And I think that's kind of what you're getting at here. But actually, I don't get a contradiction because I didn't assume these were different odd numbers. And in fact, by the pigeonhole principle, 2 of the odd numbers must be the same. So by the pigeonhole principle, we must have qi being equal to qj for some I equaling j, because there are only n possible odd integers for the qi to be, and I have n plus 1 of them. Yeah. It's good instincts to be hunting for a contradiction, but I didn't assume that they were distinct, right? Okay, so now I know that on my list of numbers, I have a qi and a qj that are the same. So now I want to compare to k sub I qi versus to k sub j qj, but remember qj is equal to qi, so I'll write qi. Can I find a divisibility relation in here? Does one of these divide the other? Right, whichever one's smaller, right? Then if ki is greater than or equal to kj, we have 2k, then we have 2kj qj, which is equal to aj, which must divide 2ki qi, which is equal to ai. And if ki is less than kj, then it's the reverse. Then ai, which is equal to 2ki qi, divides 2kj qj, which is equal to aj. All I'm saying here is that if I have two powers, one of them is going to be greater than or equal to the other, and then the smaller one divides the bigger one. That's pretty cool, huh? It's a clever proof. How do we study for these problems? Yeah, these are kind of tricky ones. My best answer is that these require some practice. And so if you're feeling uncomfortable with these problems, you should do some maybe extra problems from the textbook. This is the last section that that you need to study for, so at least there's that. I know that that's not a very good, that's not a very satisfying piece of advice, but what I can do is continue doing examples, and so that you can continue to see how these techniques are used. So the prime decomposition would be something similar to what I wrote here. Here, I just collected all of the odd primes into one term. So I just said, I've got 2 to some power times an odd number in each case, right? Now, by my assumption, each of these numbers ai are less than or equal to 2n. So each of these odd numbers must also be less than or equal to 2n, because if any of these were greater than 2n, then the whole number would be greater than 2n. So what I concluded is that this list of q1 through qn plus 1 is some list of odd integers less than or equal to 2n. But of course, they can't be equal to 2n because they're odd, right? Now, there could be repeats, and actually the pigeonhole principle demands that there's a repeat on this list because there are only n possibilities and n plus 1 integers. So I leveraged that with the pigeonhole principle to get that 2 of these odd numbers must agree. Are you okay with that? Right. And then the last thing to see is that, okay, if one of the qi is equal to one of the qj, then what's the relationship between the numbers as a whole? Well, one's a power of 2 times qi, and the other is a power of 2 times qj, which is equal to qi. Well, one of these has to divide the other. Why are there only n odd integers? Essentially, this is just saying the odd integers, which are greater than or equal to 1 and less than or equal to 2n, just go 1, 3, 5, 7, all the way up to 2n minus 1. You should count these. And it's exactly half, because in between, the next number for each of these will be an even one. 2, 4, all the way up to here, 2n. It's not a proof, but it's just a brief description of why there are only n odd integers that could be there. Is there another question or another comment? Any other questions on this proof? Okay, let's do one more. One more pigeonhole principle problem so that we can continue to get practice. Okay, that's extremely annoying probably. I'll stop that. Okay, let's do the next one. This is actually, I believe, kind of a famous one done by Paul Erdős. Who's a famous mathematician of the 20th century and a really cool individual. He spent his life wandering around the world with his mom, doing math and hanging out at people's houses and doing amphetamines. They were essential to his mathematical productivity. Well, you don't have to compete with him. You just have to admire his beautiful proof. Okay. Theorem. Every sequence, I also want to be like Paul Erdős. Every sequence of n squared plus 1 distinct real numbers contains a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. Okay, before I get into the proof of this, I just want for us to do some examples really quick. So here, this is asking for a sequence of distinct real numbers, but I would like to ask for someone to give me a sequence of 5 distinct integers. Just type them out real quick into the chat. Okay, perfect. I've got some good examples. I'll use this one first. 1, 2, 4, 3, 13. Okay, and then I'll do this one next. 3, 62, 534, 35, and 3. Naomi, perhaps we'll get to yours. Okay, yeah, actually we can. Let's do all of them. 9, 5, 3, 7, 0. So in each of these cases, let's try to find the longest strictly increasing subsequence and strictly decreasing subsequence. So a strictly increasing subsequence is just some selection of the integers here that is strictly increasing. And of course, everything is always either strictly increasing or strictly decreasing because they're all distinct. So for instance, here there's a strictly increasing subsequence of length 4, namely 1, 2, 4, 13. And so the length of increasing sequence is 4, and then the length of the longest decreasing sequence is 2, because I can go 4 and 3, but there's no other way to get a decreasing sequence here. Here, there are only 4 numbers, so I did that wrong. Okay. Here we have a very, let's see. Wait, there are 2 3s? That's wrong. Can't have 2 3s. Let's find increasing and decreasing subsequences here. So an increasing subsequence, there is 3, 7 is increasing, 5, 7 is increasing. So there are 2 length 2 increasing subsequences, 3, 7 or 5, 7. These are 2 increasing subsequences. So length 2 increasing, but there's a length 4 decreasing subsequence, namely 9, 5, 3, 0. So length 4. Is it now kind of clear with these examples what we are being asked to prove and what we are being asked to find? Notice that any number in here could be part of an increasing sequence as well as part of a decreasing sequence, right? The longest decreasing sequence in here was wait a second. Yeah, the longest decreasing sequence here was 9, 5, 3, 0, and the longest increasing sequence was 3, 7 or 5, 7. Yeah, order doesn't matter as long as I'm going left to right. That's what I mean by a subsequence. My Erdish number, I believe, is 2 or 3, I believe. I think I've published with someone whose Erdish number is 2. Yeah. So the Erdish number is, so Erdish was extremely prolific and he published a huge number of papers with a huge number of mathematicians. So it's like you have an Erdish number of 0 if you're Erdish, you have an Erdish number of 1 if you've published with Erdish, you have an Erdish number of 2 if you have published with someone who's published with Erdish, etc. So I've published with someone who I think had an Erdish number of 2. Yeah. Okay. Any further questions on either Erdish or on this idea that we're trying to explore? All right. In that case, let's do the proof. So we let a1 all the way up through an squared plus 1 be our sequence of distinct real numbers. Okay, quick aside. If I chose n squared plus 1 distinct numbers, what are my ideas for how to try to get a pigeonhole / pigeon problem? How many pigeonholes should I find in my problem so that I can apply the pigeonhole principle?
Would be n squared.
Yeah, I think I want n squared pigeonholes, and then n squared plus 1 numbers will allow me to apply the pigeonhole principle. It's true that any smaller number would work, but I want probably n squared pigeonholes. Okay. So the proof strategy is really quite interesting. Oh, and here's another thing. So we're looking for subsequences of length n plus 1. Okay. So what I'm going to do is the following. We associate to each an a tuple of integers. Bi and di, where bi is the length of the longest strictly increasing subsequence starting at ai, and di is the length of longest decreasing, strictly decreasing subsequence starting at ai. Okay, just so that we have a picture of what I'm doing here, let's play this game for this misbegotten example, but I'll add a 4 there. So for instance, if I have 3, 62, 534, 353, and 3, let's associate to each of these numbers the longest. So what's the longest increasing subsequence? Oh, not 3, 4. What's the longest strictly increasing subsequence starting with 3? Right, it's going to be length 3. Either I do 362, 534, or I do 362, 353, right? Those are my two options for my longest increasing sequence starting with 3. So my first integer is 3. How about the longest strictly decreasing subsequence starting with 3? Right, this will be a 1 because I can always take 3 as a subsequence, hiding everything else, and this is strictly decreasing, but I can't add anything else. So 3, 1 is what I put here. Okay, what is the longest strictly increasing subsequence starting with 62? What's the length of it? Right, it's going to be 2. It's either 62, 534 or 62, 353. So I have a 2. And then what is the length of the longest decreasing sequence starting with 62? 2, right, 62, 4. So a 2, 2 goes here. Okay. Longest increasing sequence starting with 534. The length of it is 1, right? Because I can't add anything else. Everything else is smaller. But what's the longest decreasing sequence starting from here now? Yeah, 3. And then here, the longest increasing is 1, the longest decreasing is 2. And then here, well, it's the end. So the only options are 1, 1, right? So with this example, anything with a 3 involved would be a either increasing or decreasing subsequence of a long enough length, because this is a sequence of length 5, which is 2 squared plus 1. So what I'm looking for is a subsequence of length 2 plus 1, namely 3. So wherever I see a 3, I know I've done it. I have a subsequence of length 3 starting here, a decreasing subsequence of length 3 starting here. Is everyone clear on how I assign these integers to my terms of the sequence? Great. Okay, so now, for the sake of contradiction, assume there is no increasing or decreasing subsequence of length n plus 1. What does that say about the possibilities for our tuples of integers? That's right. Thus, 1 is less than or equal to bi less than or equal to n, and 1 is less than or equal to di is less than or equal to n for all I. Okay, next question, and here's where we finally make our way to the pigeonholes. How many distinct options are there for ordered tuples where the first term is between 1 and n and the second term is between 1 and n? Just n? I think there are n squared, right? There are, right here, if my possible integers are between 1 and 2, the options are 1, 1, 1, 2, 2, 1, and 2, 2, right? So then there are n squared possible tuples, right? N squared possible tuples and n squared plus 1 numbers, real numbers, AI. Now what can I say? Yes, there are n squared possible tuples and n squared plus 1 real numbers. So by the pigeonhole principle, I must have an AI and an AJ, or I must have an I less than J, such that BI comma DI is equal to the tuple BJ comma DJ. So in other words, on my list, here it doesn't occur here, but I'm assuming for the sake of contradiction that all of my tuples are between 1 and n. So I must have 2 of the tuples which are the same. Okay? Do we see why this is a contradiction? This must be a contradiction because we either have AI is less than AJ or AJ or AI is greater than AJ. If AI is less than AJ, then I must have a longer increasing subsequence, like whatever increasing subsequence of length bj I have starting at aj, I can make a longer one starting at ai by going ai, comma, aj, comma, whatever this subsequence of length bj is. So these two can't be the same length because I can make a longer increasing subsequence by starting with ai. So let me write it out formally. This must be a contradiction. So there are two cases. So first assume that AI, so I'll write it down here. Case one, assume AI is less than AJ. Since, or we have a strictly increasing subsequence starting at AJ of length BJ, right? That's what it means to have the integer BJ, DJ associated to AJ. I have a strictly increasing subsequence of length BJ starting with AJ. So it goes like AJ, I don't know, Q1 all the way up through AQP or something like this. And this is a subsequence of length BJ. However, we can make a longer increasing subsequence, starting from AI, which goes AI, AJ, then the rest of this subsequence, AQ1 all the way up through AQP. This is of length BJ plus 1. So in other words, it's not possible for BI to be equal to BJ because I can make a longer subsequence that's strictly increasing by just tacking on AI in front of the subsequence of length BJ that starts with AJ. So it can't be possible that these two numbers are the same. And then the other case for a decreasing subsequence is the same. If AI is greater than AJ, then the claim is that there is an equal length decreasing subsequence starting from both, but I can actually make a long, like starting with the decreasing subsequence of length DJ, I can make a greater length decreasing subsequence by starting at AI and going AI, AJ, and then the rest of the subsequence. So it's not possible for these two entries to be equal. So a similar argument for AI greater than AJ shows this is a contradiction. Any questions here? Wow, I spent the whole time on this and no time at all on permutations and combinations. I suppose that's okay. Does anyone not understand the argument here? Why can't it be the case that AI is equal to AJ? So AI is not equal to AJ by assumption. I assumed that I had that I had n squared plus 1 distinct real numbers. So I can't have AI be equal to AJ. Right. Otherwise, this argument would all fall apart. Right. So the whole idea basically is the following. The whole idea is that if I have an AJ over here, and I have a strictly increasing subsequence that's like length 5, so 1, 2, 3, 4, 5. So this is 5 comma something, because this is an increasing subsequence. Let's say that I also have an AI, which is 5 something else. Let's say that this is K and this is K. The point is that this is already a contradiction if AI is less than AJ, because this should actually be 6, because I have a subsequence here going AI, AJ, then the rest of the 5. So the fact that both of these are 5s is impossible. Does that make sense? Similarly, if both of these have K, that means that there's a decreasing sequence starting here, 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 that's of length K. Well, now if AI is greater than AJ, then this decreasing length of K can't possibly be correct, because I can always make a longer decreasing sequence by starting with AI, AJ, and then the rest of the sequence. So this should be K plus 1. So it's not possible to have 2 tuples that are the same, because you can always add this one to an either strictly increasing subsequence or a strictly decreasing subsequence starting at AJ. So this is a really cool argument and a cool proof of a fact that would be really, really, I mean, I don't know of any other way to prove this thing. It's very beautiful. Any questions here? Yes, I have committed a crime of not discussing the binomial theorem. Well, if you want, I have old videos from last semester when I taught it, so, you know, something to do over your long break, perhaps. That's on the syllabus. I forget exactly what the percentage is. Well, it's 10:09. I want, oh yes, put up the Gradescope submission. I should do that immediately after this. And in any case, I've really enjoyed teaching this class this semester. I will split things into A's, A minuses, B's, B minuses, even B pluses. So it's A minus, B plus, B minus, C plus, C minus, etc. But I don't know how those will shake out. All I can tell you is that it will only possibly be better than normal. Like if the cutoff for an A minus is usually a 90, my claim to you is that the cutoff for an A or A minus in this class will be 90 or lower. I will not make the cutoff higher. Another way of saying I will never curve you down, only up. Okay, well, I hope that, yeah, I'm gonna get more tea. Actually, I'll just probably stay on. I'll stop recording, but thank you all for bearing with me during this semester and being patient while I sorted out all the additional things like posting assignments and posting submission places and things like that. I've enjoyed having this class, so yeah.
I have a quick question.
Yeah, sure. I'll probably just
So,
stay on actually and make tea, but go on. What's your question?
As you were talking about assigning a